Question is asking us to find the voltage across the capacitor from when time is greater than 0 and find the current flowing through this resistor from when time is greater than 0. And to do that, we're going to need these two equations up here, where the voltage across the capacitor is equal to the voltage across the capacitor when time is equal to 0, and the exponential of the negative time divided by RC. And the current equation is current is equal to the voltage across the capacitor at time equals 0 over the resistance of the circuit, and times the exponential of negative t over RC. All right, and now looking at this circuit right here, we know that this switch right here, when time is equal to 0, it's going to open. So that means anytime after time is equal to 0, this half of the circuit is going to become source free, and over here it'll be 0 amps flowing through it, so we don't need to account for that when time is greater than 0. All right, so first I'm going to solve the circuit for V0. So basically what I'm going to do here is going to find when time is less than 0. And to do that, we know that this switch opened up, so we just have to make this circuit basically a DC circuit. All right, so I've redrawn the circuit for when time is less than 0. So basically what I did, I just took this switch and made it a wire. And we know that capacitors under the DC condition will become an open circuit. So that means over here, the current is going to be 0 amps, and same with down here, because the current can't come across this capacitor. So this is going to be 0 amps as well. So that means the voltage across this resistor is 0 volts. And now, what we're trying to do when time is less than 0 is find V0, or V0 of C. So in order to find V0 of C, we can just, it's just going to be equal to the voltage across this resistor or this resistor, because they're in parallel, so their voltage will be the same. But in order to do that, we need to find the voltage across it. And I'm going to elect to do voltage division. Well, because these two resistors in parallel is equal to 4 ohms. So this voltage across here when time is less than 0 is simply going to be equal to 4 over 4. 6 plus 4 plus 2 is 12 times 15. And that's going to be equal to a number. That's going to be equal to, all right, so that's going to be equal to 5 volts. All right, so now that we have that, we already have basically half our equation done. All right, so I've redrawn the circuit in terms when the time is greater than 0. So what that means, I just took the switch and left it open. So what does that mean for this half of the circuit? That's an open circuit. That means there's no current flowing through here. And there's no current flowing through here. So basically, our circuit went from looking a little complicated, and now we can just erase this half. All right. So now what we're trying to do when time is greater than 0 is solve the other half of this equation of E is equal to negative time times over RC. So our resistance in the equation has to be the equivalent resistance of the circuit. So that's pretty easy to compute because these two are in parallel. We already know this is 4 ohms. And then we can just do series, and they're in series, so we just add them up. So our RTH is equal to 10 ohms. All right, so now what we need to do is compute the RC. So to do that, I'm just going to do 1 over RC, which is going to be equal to 1 over 10 times 40 times 10 to the negative third, because our capacitance is 40 microfarads. So this is equal to 2.5. So now we finally can write our equation for the voltage for when time is greater than 0. So V of t is going to equal to V naught, which we saw was 5 volts, times the exponential of the negative t to the RC. So that'll just be negative 2.5 t. So now we're already done we're halfway done our question. Are also questions asking us to find the current flowing through this resistor. All right. To do that, we need to first find the current flowing to the capacitor, which we already denoted as the current is equal to V naught over R times the exponential to the negative t over RC. All right. To do that, our I of C equation is going to equal V naught, which is 5 over 40 times 10 to the negative third times e to the negative 2.5 t. All right. And then doing a bunch of nerdy math, you get this is equal to negative 0.5. Oh, I made a mistake. We need to find that was totally incorrect. Whatever, we're doing one take. So the real equation for finding IC of t is going to be equal to the capacitance of a capacitor times the derivative of the voltage. So I'm just going to compute V prime of t. V prime of t is equal to negative 2.5 times 5e to the negative 2.5 t. All right, now we just plug in our capacitance, which we already know is 40 times 10 to the negative third times negative 2.5 times 5 e to the negative 2.5 t. So that means this is all equal to 0.5. I think it's negative 0.5 times e to the negative 2.5 t. Well, and now we can do current division to find I sub 1. To do that, I sub 1 of t is going to be equal to the other resistor, so it's going to be our 6 ohm resistor, over 12 plus 6 times I sub c of t. All right. We also need to pay attention to that our current, our current of the capacitor is flowing in, but our current for the resistor is flowing down. So that means they're going opposite ways, because by convention, the current should be flowing out of the positive terminal. So that means this whole equation needs to be to the negative. All right, so now we just basically plug and chug. So this is going to be equal to negative 1/3 times negative 0.5 e to the negative 2.5 t. So this whole equation is equal to 0.1667 e to the negative 2.5 t. Oh, and of course these equations are in amps. All right. So our two answers that we needed, we found v sub c of t, which was this equation right here, and find I sub 1 of t, which is this equation right here. All right, that's our first problem. Let's move on. All right, so here is problem 2. This is also the practice problems for the recitations. So in this problem, we have another switch that when time is equal to 0, it opens up. So that means when time is greater than 0, this half of the circuit becomes just an RC circuit with no source. But for when time is less than 0, it does have a source and becomes a DC circuit, which we know how to solve pretty much. But this problem is asking us to find the voltage across the capacitor for when time is greater than 0, and find the voltage across this resistor when time is greater than 0. So just like the last problem, but we're just solving for voltage instead of current. All right, so this is the circuit for when the time is less than 0. So that means that this switch up here just becomes a wire. And with that, we know that this circuit is now under the DC condition. So that means that this capacitor right here becomes an open circuit. And with that knowledge, we know that the current flowing through here is going to be 0 amps. So that means the voltage across this resistor is 0 volts. Will help us later. All right, so the goal of when t is less than 0 is to find the voltage across the capacitor at time is equal to 0. So to do that, we know that the voltage across this capacitor is just going to be equal to the voltage across this resistor. So to do that, we just need some simple current division. So it's going to be we need to find the current flowing through here. So the current is going to equal to the other resistor, so it's going to be our 4, plus our 12 plus 4 is equal to 6 times 6, because our current source is 6 amps. So to do that, this is going to be 24 over 16, which is going to be equal to 3 over 2, which is equal to 1.5 amps. All right, and now we just need to find the voltage across this resistor. So it's just going to be 1.5 times our 8, which is equal to 12 volts. And this is equal to V of C of naught. All right, so now we have everything we need to solve for on this half of the circuit. Now let's go on to when time is greater than 0. All right, so here's a circuit for when time is greater than 0. So that means that this switch is still open, which means that this half of the circuit can just be erased and gone with because there's no current flowing through it. All right, so now the point of solving for when time is greater than 0, that we want to find our 1 over RC. So to do that, first we need to find the equivalent resistance, which is pretty easy to see. It's just 12 plus 8. So our RTH is equal to 20 ohms. And now what we need to do is compute 1 over RC, which is going to be equal to 1 over 20 times 25 times 10 to the negative third, which this is all equal to 2. All right, and now we have everything we need to solve the voltage of the capacitor. So the voltage of the capacitor is going to be equal to our V naught, which we already decided was 12, times e to the negative 2, which is our 1 over RC, negative 2t. All right, and now we're almost done. We just need to do one more thing, is that it wants us to find the voltage across this resistor, because it says find V1 of t for when t is greater than 0. So to do that, we can do some simple voltage division. So V1 of t It's going to equal to our resistor that we're looking at, which is 8, over the total, which is 20, times our voltage. So it's going to be times 12e to the negative 2t. And this is all equal to 4.8 e to the negative t. All right, and that is our second problem done. All right, so this is the last practice problem for RC circuits. It looks a little bit more complicated, but we're going to simplify it to make it look a lot easier. So to do that, we're basically going to take this portion of the circuit and basically make it into just equivalent resistor using Thevenin's theorem, which we'll solve out. It looks a little more complicated than it really is. It's more like a last chapter problem combined with this chapter's problem. But yeah, just stay calm and we got this. All right, so this is our setup for Thevenin's theorem to solve for RTH. To do this, I basically make this so this is t is like greater. This is t is greater than 0. So that means up here, our capacitor became an open circuit, which we know how to solve open circuits already with Thevenin's theorem. So in order to find RTH, I introduced this current source in place of the open circuit of where the capacitor would be. And now, in order to solve this, we can just do a simple KCL. So we're going to have 1 amp going in, and then 1 IX and plus 2 IX going out. So 1 IX plus 2 IX is equal to 1. So that means IX is equal to 1 over 3. And then we can identify that VO is in parallel with this dependent source and then these two resistors. So we can simply find VO by just computing Ohm's law. So VO is going to equal our resistors in series, so it's going to be 30 times our current flowing through that, which we already know is IX. So it's 1/3. So that VO is equal to 10. And therefore our RTH, just like Thevenin's theorem, is going to equal to our V0 over our I0. Our I0 was just 1 amp. So that's going to be 10 over 1, which is equal to 10 ohms. All right, and then with this information, we'll be able to rewrite this whole green part of the circuit as just equal to 10 ohms. All right, so this is the circuit redrawn with that. We know that RTH, or this whole portion of the circuit inside the green bubble, is equal to 10 ohms. All right, so now what we just need to do is solve for V of t. All right, to do that, I'm not going to redraw the circuits because it's pretty easy to see everything. So when time is greater than 0, this switch remains open. So that means this whole half of the circuit is not part of our circuit. So that means our RTH is equal to 10 ohms. So with that, we'll be able to calculate the RC. So our 1 over RC is going to be equal to 1 over 0.5 times 10, which is equal to 1 over 5. Yes. Which is just equal to 0.2. All right. And now we need to solve for the circuit when time is less than 0. So when time is less than 0, this switch right here becomes just a straight wire. This circuit works under DC conditions. So that means that this capacitor is just an open circuit. And just to find the voltage across this resistor is just equal, the voltage across this capacitor is just equal to the resistor, the voltage across either resistor. So you can do this 2 different ways. You can simply just find the equivalent resistance of the circuit and then do Ohm's law, which I guess that's what I will do. So 10 and 40 in parallel So our REQ is going to be equal 10 and 40 in parallel, which is just equal to a number. It's equal to 8 ohms. So then with that, we can easily find our VC. VC is going to be equal to this, basically just Ohm's law. So it's going to be equal to our 2 amps times our equivalent resistance, which is equal to 8, which is equal to 16 volts. And now that we have that, we can solve for V of sub C of T. So this equation is now going to be equal to our V sub naught, which was calculated right here. So it's going to be equal to 16 times E2 times our 1 over RC, which is going to be 0.2 T. All right. And finally, we need to find the current flowing through the capacitor. No. The current flowing through IX. All right. So how they did IX is that IX of T is going to be equal to our V sub naught, so it's going to be our 16 volts, over the resistance of this half circuit, which is going to be 30 times our this half of the equation, so e to the negative 0.2 t. So our final answer for this is just this, because who wants to do some math? All right. So this problem is probably the most complicated because it has a dependent source, and we use Thevenin's theorem to make it 10 ohms, but just stay calm and work your way through these. Good luck.